Looked at the Matthews equation and last time the forced Duffing equation, and now we're going to look at a third very interesting and fun to play with mathematical model, and that is the Saltzman-Lorenz model. Most people just refer to it as the Lorenz model because he's the one who gets all the credit for the interesting things I'm going to show you in this video, but the model itself was actually developed a couple years before and published by Saltzman. So Lorenz used Saltzman's model. The interesting results do come from from Lorenz. So this is building on the deterministic chaos that we discussed briefly in the context of the forced Duffing equation in the last video. It's a very interesting history behind it. There was a meteorologist named Edward Lorenz at MIT back in the 1950s and early 1960s that published the paper. Originally they published was dated 1963. And so he was a researcher trying to better understand atmospheric dynamics. There was some serendipity, which is just a fancy word for chance, in his discoveries, but you have to give him credit for the astute observation and creative investigation. What he found and his conclusions really went against the prevailing wisdom at the time in terms of how differential equation solutions can behave and so on. So it was pretty revolutionary at the time, and it was not immediately and widely accepted. The problem that he was looking at is actually a very simple one. It's called Rayleigh-Benard convection, which I'll get at in a moment. What he's really looking to do was develop models for predicting atmospheric dynamics, so basically the weather. And obviously weather prediction is something that's changed dramatically over the years and decades. It's still not perfect, nowhere near perfect, and some of Lorenz's work explains why that is the case and why we don't have long-term weather predictive models that are accurate, even with the modern supercomputers and so on that we're using today. So let me describe this Rayleigh-Benard convection concept. Again, very simple. You have two parallel flat plates. If you had a higher temperature at the top plate, lower temperature on the bottom plate, then the fluid would not even move. When you have a fluid in between, air, say. You put a fluid in between, hot at the top, cool at the bottom, because hot air rises, the fluid doesn't even move, and it's thermally stratified and stable. Now if you reverse it so that the bottom plate is heated and the upper plate is cooler, so that'd be like the surface of the Earth being warm and the upper atmosphere being cool, which is normally the case, then the fluid inside, in between the two plates, will start to move. It starts to convect, which is what we call convection. So what he was looking at was this very, very simple problem. It's governed by Navier-Stokes equations, which you 313 students will see or have seen, and along with coupled heat transfer because of the different temperatures. So it's a very simple problem, and he was just trying to develop some models that in the early 1960s could be solved on a computer that would be relevant to atmospheric dynamics. But what he found through these numerical solutions of these seemingly simple equations, which I'll show you in a moment, turned out to have very far-reaching effects on our understanding of nonlinear equations and the systems that they govern. So here is the model. It's a simplified Navier-Stokes equation model along with heat transfer. As you know if you've seen them, Navier-Stokes equations are partial differential equations. I actually showed them to you at the beginning of this chapter in vector form. So these are very complicated nonlinear equations, but if you make a whole bunch of simplifications for this particular Rayleigh-Benard convection problem, you arrive at three coupled nonlinear first-order ordinary differential equations. And here they are. Now, as you would imagine, there's a great deal of simplification. There's a great deal of physics that has been jettisoned from the real model, different PDE model. And you can see the equations look actually not that much different than what we've looked at and played with a bit earlier in the semester. So the x, the y, and the z are the dependent variables, and they contain information about the fluid motion as well as the temperature distribution. I won't get into the details of that any more than to say that changes in x, changes in y, changes in z are related to changes in the motion and temperature of the fluid. Then the independent variable, of course, is just time. These are ODE, so there's only one independent variable. Then on the right-hand side, you see a series of three parameters. So there's sigma. Sigma is the Prandtl number of the fluids. That's just a property of the fluid. B is the aspect ratio of the convection rolls. So if you have these two surfaces, you get convection rolls between them. And you could have short, fat convection rolls. You could have tall, skinny convection rolls. And so the B quantifies that aspect ratio, the shape of the convection rolls. And finally, R, right here, is known as the Rayleigh number. So in fluid mechanics, you've heard of the Reynolds number. In convective heat transfer, there's the Rayleigh number. And here that's given by R. And that's basically a non-dimensional temperature difference. So the bigger the temperature difference between the two plates, the larger the Rayleigh number is, and we'll take a look at the effect of that. Now, if you take a closer look at these, at the first equation, for example, there's nothing nonlinear in there at all. It's just minus sigma x and plus sigma y. So that's linear. These two terms are linear, and this term is linear. The only nonlinear terms are these two. There's an x times a z and an x times a y. And so naively, you think, well, so what? How much difference can that make? And it turns out to make a significant difference. And this is the thing that people in the mid part of the last century did not really appreciate. Okay, so we're going to look at solutions of this system of three coupled ODEs. Very easy to solve in Mathematica is what I've done here. Very easy to solve in Python with built-in functions. So I'm going to start off with a low Rayleigh number, so 10, you'll see here. And the sigma and the B are going to stay the same. So the Prandtl number and the aspect ratio are not going to change until I say they do. So for most of the rest of this video, sigma is 3, B is 1. And the only thing we're going to change is the Rayleigh number. And again, when you think of Rayleigh number, just think of the temperature difference. So Rayleigh number of 10 represents a relatively small temperature difference. Okay, now the initial conditions will be 6, 6, 6. Yeah, no, that's pretty scary. So there's nothing special about 666 in this case, but so that's our initial condition. At t is equal to 0, x is 6, y is 6, and z is 6. So if you compute the solution, as you normally would, a system of three equations, here's a plot of x, y, and z as a function of time from 0 to 30. All of our calculations are from 0 to 30. And you just see these wibbly-wobbly solutions. So x and y are down here, and z is actually this one up here. And you'll see they just look like damped oscillations, very similar to what we had for the Duffing equation with damping. So no forcing, no nonlinearity, just damping. So this is what we would say is very typical linear type behavior. There's nothing particularly exotic or exciting about this. You can see that as time goes on, these are settling down to what we call stationary solutions. So actually that's 3, 3, and 9. X and y are equal to 3, and z is equal to 9. And then they just stay there for all time. So that's just a stationary solution. Doesn't change with time any longer. Boring, again, very typical of a linear behavior type situation. It's very interesting to look at these in the phase space. It's now a three-dimensional phase space because we have x, y, and z, not just x and y, or x1 and x2, or u and u dot, or whatever the two are. So this is for the same case with r is equal to 10. We start off with 6, 6, 6. That's the last time. So we start off right here at 6, 6, 6. And then this blue line represents the trajectory in the x, y, z phase space. And you can see it spiraling into the center, which is x is equal to 3, y is equal to 3, and z is equal to 9. 3, 3, 9. I think that's what I said, yep. So again, very linear type behavior, nothing terribly exciting. Okay, let's increase the Rayleigh number to 10, from 10 to 27. So we're increasing the temperature difference between the two surfaces. Once again, plot x, y, and z as functions of time till t is equal to 30. And now you can see things are quite different. They are not settling down to stationary solutions for x, y, and z. And for example, if you look at these two at the bottom, which is x and y, so you'll notice, of course, this is this is 0, so x, y, or z is equal to 0, and positive and then negative above and below. So what you'll see is that sometimes these are negative, sometimes they're positive, negative, positive, negative, positive, negative, positive, and they just kind of seem to jump back and forth from one side of 0 to the other somewhat randomly. Now, what does it mean to jump from positive, negative, negative, and positive? What that means is when you're negative, that means the convection rolls are going, I think, one way or the other, clockwise or counterclockwise. And then when it goes positive, then that means it has switched directions and it's now going the other way. So if you look here, it's going round and round and round several times, the same direction, and then all of a sudden it switches direction. And then it switches direction back, switches direction several times, and back and forth. So that's unusual. That's certainly not linear type behavior, and it's very different than the lower Rayleigh number. Here's what it looks like in the 3D phase plane. So here's 666, and it's hard to tell from this, but it actually goes around one lobe, and then switches over to the other lobe, switches back to the other lobe, and it's going back and forth between these two lobes. The two lobes represent, again, positive, negative, counterclockwise and clockwise rotation of the convection rolls. So now this might look familiar. You've seen this probably in books and different places. This is the famed Lorenz Attractor, which we'll talk more about. And we'll talk more about why we call them attractors and strange attractors. We mentioned them in the last video. We'll talk more specifically about it here. Okay, so again, it is called the Lorenz Attractor. It comes from the Lorenz model. It is a strange attractor, which we briefly mentioned last time. So let's talk about attractors more specifically than we did in the previous video. So an attractor is a shape, it's a region in the phase plane that, as long as you start your initial conditions in the basin of attraction, the solution will get kind of trapped. It's kind of like a body coming in towards something with gravity in space, and it gets trapped into its orbit. So it's kind of like that. As long as you're in the basin of attraction where you start, you'll eventually get drawn into or attracted into this region. So we started out here, but it gets attracted into this strange attractor, the Lorenz attractor. So whether I started here, 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 doesn't really matter. We're going to see the same basic strange attractor structure developing. So that's an attractor. Now we call it strange because it has a geometrically complicated shape. So you'll remember in the force-Duffing equation we had that beautiful set of dots from the Poincare section, and that's obviously very geometrically complicated. Here it's not as geometrically complicated, but nevertheless it is somewhat complicated. It's kind of this, looks like this butterfly wing sort of shape. So that's what makes it strange, and then it has various other properties that we'll illustrate in a little bit. Once again, the two lobes represent the clockwise and counterclockwise rotation. So as it switches, you can see it switching back and forth here. Not every time, it's not one around the other, but it's going around one several times and switching to the other one and then switching back. So you can see every time it's switching back and forth, it's actually changing the sign of rotation of the convection rolls, which is a seemingly unexpected behavior. And again, this is coming from a very simple set of nonlinear ODEs. Okay, one of the properties of deterministic chaos is a sensitivity to initial conditions. We now know this and kind of take this for granted, and we call it the butterfly effect. There's even a movie called The Butterfly Effect. But at the time, this was really not appreciated at all. It came about this is the serendipity for Lorenz. So what he did was he had a solution going. These took a long time. They're not like today, you hit the go button, you get the solution immediately. So he had a solution going for X, Y, and Z as function of time, so developing. And the next day he wanted to come in and restart a calculation that he had already been doing, but he didn't want to go all the way back to t is equal to 0 and waste all the time to get to some intermediate point. So instead he just took a read-off, a printout of the solution at a particular time. And then he put those in to the computer as the initial conditions to start from that intermediate time and go forward. The problem was the following. So the computer was using 6-digit math. So a number that, for example, might have been 0.753441 in the computer, he was only printing out 3 significant figures. So that would have been printed out as 0.753. So he put in 0.753 as the initial condition, thinking, well, that's close enough to this actual number that it should give me the same solution. But then it didn't. So it went on for some period of time, tracking very closely with the previous solution. And then after a long period of time, they diverged tremendously. So there was a big change in, whoops. Oh, what did I do? Next. Well, that's interesting. Let's